All right, Chem 1110 students, we are going to look at this quantum theory and quantum numbers in a little bit more detail. This is what I originally thought of as the second part, but the videos got to be too long. So we ended the last video starting to look at the notation that is used for orbitals. And so we're going to move on with that, and we're looking at atomic orbitals and what they mean and how we designate them. And so we're going to look at s orbitals, and in an s orbital, n is equal to an integer, and it's going to be the row in the periodic table, and L is equal to 0. That is what gives it that spherical shape. And so 1s is smaller than a 2s, it's smaller than a 3s, and these correspond to these rows in the periodic table, first, second, and third. So this is our notation again, and so we say it starts with the principal quantum number. It's 2. That means we know we're talking about the second row, and the s means that L is equal to 0, the angular momentum, and therefore m sub L can only equal 0, meaning there's only one orientation possible. And if you look at these, it's a pretty fancy graph that really doesn't mean much to you probably, except for along the bottom of that graph you can see these would be the plots of the value for the Schrodinger equation, and they are all spherical. So in the middle is like a quarter cross-sectional of a sphere, and you can see that they get bigger as you go from 1, 2, and 3. So now we're going to look at the next kind of orbital, and these are the p orbitals. So in order to have a p orbital, n still has to be greater than 1. So it could be 1, 2, 3, 4, 5. And if n is at least 2 or bigger, then L can have two values. It can have a 0 and a 1. If it has a 0, it's a spherical orbital. If it's 1, then m sub L can be -1, 0, and 1, meaning you have 3 equivalent orbitals, and these have been called p orbitals, and they look like this. Now, A is the actual result you get out of the equation, and we saw that before. So it's this electron density that is on the z-axis above and below the xy plane. And then in the B part where they have PZ, PX, and PY, these are a bit more concrete looking, and it just shows you the electron density on either side of where X and Y are both, and Z are all 0. It doesn't mean the electron travels in, like a figure 8, but it just says that the electron can be on either side. Okay, so we have another atomic orbital we're going to talk about, and those are the d orbitals. So they go in this order. The s's are round, the p's are like dumbbells, and then we have d's. All right, so in order to have a d orbital, n has to be equal to or greater than 3. If n equals 3, then L, remember, is n-1 going down to 0. So it can be 0, 1, or 2. And if it's 0, then m sub L is 0, and there's your s orbital. If L equals 1, then m sub L can be -1, 0, or 1, so you have 3 p orbitals. And if L equals 2, then m sub L can be -2, -1, 0, 1, and 2. So there's 5 different ones, and that's where you get your 5 equivalent d orbitals. And the d orbitals, well, I'll tell you how these correspond to the periodic table in a bit. But here are these shapes, and they are kind of strange. You don't have to memorize these. You need to know the shape for an S or a P, but you just need to know that there are some d orbitals, and there are 5 of them. Okay, moving on. So we want to look at the energies of these orbitals in the hydrogen atom. The hydrogen atom is special because it only contains 1 electron. And so this would be all the potential shells for the S, or for that 1 electron in a hydrogen atom. So it's going to be down here in the 1s, and then you see there's some energy levels for that second level, which are used by the elements in the second row, third, and the fourth. And you can see how you have 1 S, but you have 3 Ps, you have 5 Ds, you have 7 Fs. We didn't go into talking about those shapes. They get pretty complicated. And so the next one, this slide talks about the 2s subshell, the 2p subshell, and gives you those quantum numbers so you can kind of study that. Same thing for the n equals 3 subshell. So the 3s and the 3p and the 3d. So there's a question here. List the values for n, l, and m sub l for each of the orbitals in the 4d subshell. Okay, so the first number tells you the principal quantum number. So this is obviously 4. It's the 4th row. And that letter tells you what kind of orbital it is, and that's going to tell you what the L is. So in this case, 4D says it's a principal quantum number of 4, and since it's a D, that angular momentum quantum number equals 2. Remember, if L equals 0, it's spherical. If L equals 1, it's a P. And if L equals 2, it's a D. Okay. The possible m sub l's, meaning there's 5 equivalent d orbitals, are -2, -1, 0, +1, and +2. Okay. And here's that chart we saw before, and you can just use this to sort of try and verify your results. It was 4D, so the n equaled 4, and the D subshell is up there when L equals 2. All right, moving on. We are going to look at the first few elements in the periodic table and look at how their electron configurations are designated. So this is a ground state, or a picture of the ground state of the hydrogen atom. The electron is in the 1s, it's in that top row, and we showed that the electron is sort of a half arrow, and it's pointing up. But the notation is still a 1s1, and that superscript 1 says that there is only 1 electron. Now, it is possible to promote that electron to an excited state, put it in a higher energy level. You have to do that by introducing energy, maybe via electricity or via heat. And in this case, a possible excited state would be a 2s1, because you've moved that 1 electron to the 2s orbital. The superscript 1 means there's only 1 electron. Okay, we're going to look at some of the other ground states, though. Oh, pardon me. We're going to start with helium. So it has 2 electrons. It's the second element in the periodic table. And I just want to show you this Pauli exclusion principle. And it says no 2 electrons in an atom can have the same 4 quantum numbers. And so the difference because they're both in the 1s, and that superscript 2 says there's 2 electrons. But in the bottom right-hand corner, I show you the quantum numbers for each of those electrons. And I have 1/2 arrow pointing up, 1/2 arrow pointing down. So that specifies 2 electrons, and the fact that they are upside down from each other means that their spins are different. So that electron spin magnetic or quantum number, pardon me, m sub s, one is a positive 1/2, one is a minus 1/2. The reason they can be in the same orbital is that, a spinning charge creates a magnetic field. One where the north would be up, the other one is where the north would be down. And so, therefore, even though like charges repel, in this case, the magnetic field causes them to be attracted to each other, and therefore they're compatible. Okay, when we go to lithium, which is the beginning of the second row, but it has 3 electrons, we now can also talk about the Aufbau principle. And I'm sorry, but these Aufbau is German because a lot of this work was done in Germany. So in this case, you have 3 electrons. You can only put 2 in the 1s orbital, so it's a 1s2. And that third electron then is up in the 2s. And that is why this appears in the second row of the periodic table. And what this says is that electrons are added lowest energy level first. And once again, as we talked about at the very beginning, nature prefers the lowest energy level possible. So they go into the 1s, 2 of them do, and we call that spin paired. One is up and one is down, and then the other one goes into the 2s level. So the designation for lithium, showing where all 3 of its electrons are, is 1s2, 2s1. All right, and we're going to move on. Beryllium has 4 electrons, and so this is a 1s2, 2s2. Once again, it follows that Aufbau principle, and you can see that the Pauli exclusion principle is also met because those electrons, the 2 in the 1s and the 2 in the 2s, are spin paired. And the other thing I will point out is that in the example of beryllium, and we'll talk about this a little bit more, because we have multiple electrons, those p orbitals are slightly higher in energy than the s, and we will come back to that a little bit later as we finish going through this second row. So we have boron with 5 electrons, 1s2, 2s2, 2p1. So those superscripts have to add up to the number of electrons you have. 2 plus 2 plus 1 gives you 5. The next one is carbon. It has 4. And now we have Hund's rule. I like to call it the empty bus seat rule, because when people get on a bus, if there is someone already sitting in a seat, you don't tend to sit down next to them. You go sit in your own seat. So carbon has 6 electrons, so it's a 1s2, 2s2. That uses 4 of the electrons, and now we have 2 more, and they go into separate 2p orbitals. These all have the same energy, so they can pick and choose, but it basically says they're going to spread out if they can, and that's why I call it the empty bus seat rule. So we move on. Nitrogen has 7, 1s2, 2s2, 2p3. Fluorine has 9, and I didn't mention in the last one, when you have your electrons singly in the p's, those are diamagnetic, and fluorine, as you can see, is paramagnetic because, paramagnetic because it has an unpaired electron. And then if we look at neon, all the energy levels, all the orbitals are filled, and they're all paired electrons, so this is diamagnetic.